So in this video, I'd like to spend the time trying to explain to you the binomial theorem, where it comes from and how we can use it. So it is in front of you. You can see it there in the blue box. However, we're going to leave that and we're going to try and work on some math to help understand what this is all about. All right. So let's start off with Pascal's triangle. And we know this. We've seen it lots and lots and lots already. And we get the next terms, don't we, by adding the ones above, and we could go on like this forever and ever and ever. So we've also seen some notation, and I mentioned this in a previous video, that we have a typical term. Let's just take that 4 for a second. That is on the fourth line of Pascal's triangle, where n is 4, and it is in position 3 because we start from 0 here. That's 4, 0, 4, 1, 4, 2, and so the 4 there, look, is 4, 3. So if I was going to write Pascal's triangle in that notation, I would start like this. So I'd have 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, and I can keep going again forever. Let's just do one more line, shall we? 3, 0, 3, 1, 3, 2, 3, 3. So we could continue writing like that. That notation is very useful. We're going to leave that there. Now, let's go and think about a totally different area of mathematics now, and let's look at combinatorics. So combinations and combinatorics, generally as an idea, is all about how we select objects and choose things, right? So this is going to make no sense as to why I'm talking about this right now until a little bit later on in this video, but let's just have a quick example, right? So imagine I have, I don't know, 3 counters. We have a red counter, a blue counter, and a yellow counter. So I have 3 objects. Okay, so imagine I want to select two of these objects. So I've got 3. I'm going to select 2, but I don't really care about the order. Okay, so order not important. How many ways are there of doing it? So let's count them, right? Let's think about this. Well, I could pick a red one and a blue one, or I could pick a red one and a yellow one, or I could pick a blue one and a yellow one, and that's it really, okay? And so the answer to that question was there are 3 different ways. And you're going to see where this is going in a minute because I write this as 3, 2. Where that top thing there is the number of objects I started with, and that lower number is the number that I wanted, right? 3, 2. And of course, 3, 2 is 3. Now, you're already hopefully thinking, well, hang on a second. Does that match what we did earlier? Okay, 3, 2 is that position there, isn't it? And it was a 3. So it worked. There's a link here between combinations and the numbers inside Pascal's triangle. So let's try this again, right? Let's try this again. Let's just see if this carries on working. So let's this time pick 5 objects. Imagine we've got some tokens or something, and they are labeled 1, 2, 3, 4, 5, right? And maybe I want to pick 2 of them. Right? Maybe I want to pick 2 of them. So let's figure out, okay, how many ways there are of picking 2 of them. So let's start with 1 and 2. In fact, why don't we keep the 1 fixed and do this in quite a clever, organized fashion. So all of the ways of doing this with a 1 in there, I'll give them there, look, 2, 3, 4, 5 being the other numbers. Right. Okay. So what about then if we had 2 as that first number? Well, we've already picked 2, 1. So I guess we're going to have 2, 3, 2, 4, and 2, 5. Okay, so that's another 3. Let's just put these up, look, so we can keep this organized and we know what we're doing. Right, so now let's pick, 3, and I guess we can pick a 3 with a 4 or a 3 with a 5. We've already written down the other combinations with the 3 in, the 3, 2 and the 3, 1. And then with the 4, the only one left is the 4 with the 5, okay? And of course, all of the 5 combinations have already been used. So how many was that? So 1, 2, 3, 4. 5, 6, well, 3 there, 2 there, and 1 there. So if we add these up, we're going to get 10. Okay, so what have we learnt? Well, the number of ways of choosing 2 objects out of 5, so 5, 2, is 10. Does this match up with our Pascal's triangle? Okay, well, we're going to need another line for that. We haven't done the 5th line yet, so let's go back to our triangle. 1, 5, 10, 10, 5, 1. And we were looking for 5, 2. So 5, 2 is here. And yes, it is 10. So this really works. Now, this particular area of mathematics actually has a formula that we can work out, all right, that involves n and r in it. So we can find this formula for n and r. And I don't want to go into detail, particularly in this video, as to how it comes about. But if you think about it hard enough, I'm sure you're going to see it. It is n factorial over n minus r factorial, r factorial. Okay, so this is a way that we can find this number of combinations. So we can directly apply it to finding positions in Pascal's triangle, and that in itself means that we can apply it to working out the coefficients in binomial expansions. Okay, so now we know all this, we can put it perhaps together, and we can say that a plus b to the power of n is equal to, right, and so of course the first one, if we're on the nth row of Pascal's triangle, because we've got that n at the top there, we've got n0 a to the n plus n1 a to, well, remember the pattern, it was always 1 less than the original starting power of a, wasn't it? It's going down by 1 every time, but we're increasing the b's, so we're going to have b there as well, right, plus n2 a to the n minus 1, and that b is increasing by 1 like this, right? So this is helping us to write down a new format for Pascal's triangle. Maybe we could think about a generic term, right? Okay, so somewhere in the middle of this would be a coefficient of nr, and we would have a to the power of something and b to the power of something. Well, if we go back to our Pascal's triangle, that value of r is always going to be the same power of b. So we can jump straight in and write that there. And the powers always add up to n. So that means that a to the power of n minus r is the only thing that's going to work there. So that is going to be a general term that we can have inside of our expansion. And I guess the final term we should probably write down would be the last one, so nn. So the last one, for example, I know it's always 1, but 6, 6 or 5, 5, right? There's no values, no power of a, so it's just b to the power of n. Okay, so that is a quick version of the binomial theorem, okay? A plus b to the power of n can be written like this. And the great news for us is, because there's a formula for finding these coefficients, that means we can use our calculators to find them. So if we wanted the 57th line of Pascal's triangle, we don't need to draw it out. We could use our calculators to find it when n is 56, or 57, sorry. So on your calculators, okay, if you have a TI-84, if you press math and then scroll across to the probability functions, okay, if you go down, NCR is the one we want. That's the combinations button. N choose R is often how it's said. And you type in the first value is N, the second value is R, right? So 5 choose 2 or 5 NCR2 is 10, as we've just seen. So check you can find that and do that on your calculator. Okay, I think in the next video, we'll do some examples.